chapter 11 is all about an introduction to calculus. So if there's a chapter that will help you next year in calculus, this is definitely it, because we're going to cover, basically calculus covers three main topics. There are limits, there are derivatives, and there are antiderivatives or integrals. And then there are applications of those things that you spend a lot of time on. But those three concepts, basically, if you master those three concepts, then the rest of calculus becomes quite a bit easier. So we're going to touch on all three of those concepts in class this week and next week. So, um, but yeah, so we're going to start off with limits. That's the very first idea of calculus. Now, calculus has this bad name as, you know, being the super hard math. Like whenever anybody equates something with difficult, they say, you know, it's like calculus, right? And it's basically the second most common comparison versus like rocket science or something like that. But calculus itself is not that bad. It's really what it's doing is going to take everything that you've learned so far and then add this concept of infinity to it. And in the infinite case of things, sometimes it's not as intuitive as you might like, but basically it's just everything we've done before with adding in the concept of infinity. So limits are kind of the first idea of that. So suppose that f is a function defined on some open interval containing the number a. The function f may or may not be defined at a. The limit notation, so limit as x approaches a of f of x equals L. So that's the notation for the limit. So that's just saying as x gets closer and closer and closer and closer to a, f of x gets closer and closer and closer to L. It doesn't actually ever have to hit it or anything like that, but it just has to get closer and closer and closer. So just real quickly, let's just kind of do it using a table. So if we go ahead and say limit as x goes to 3 of 4x squared. So let's punch in 4x squared here. Let's go to table setup. Let's start it. We want to get to 3, so let's start at, say, 2.9, and then go by 0.1. So, so now let's take a look at our table. So second table. Oops, I meant to go by 0.01. So let's actually do that real quick. So if we look at this, as we get closer and closer and closer to 3, what's getting closer and closer? What's the y value getting closer and closer to? Well, it looks like it's getting closer and closer to 36, right? So if I were to look at that, I would say, well, this looks like it's 36. Now we haven't proven anything or anything at all right now. We're just exploring to get the idea of what a limit is. But that ends up being the actual limit for sure. But we haven't proven anything yet. We're just exploring. So let's try. Make sure you're in radians whenever we're doing anything in calculus. It has to be in radians, not in degrees, because again, all the reasons we talked about before, radians are an actual thing, whereas degrees are kind of a man-made construct. So let's take a look at, say, let's do cosine of x minus 1 over x. And we want to, as x goes to 0, so let's go to table set. Let's just start at, say, negative 0.1. And then let's go by hundredths again. So if I look at this table, notice, as I scroll down, notice at 0 there's an error, right? Because I can't divide by 0. But what does it look like the y values are getting close to as x gets close to 0? We're getting smaller and smaller and smaller, and then we get negative. So it looks like we're going to get to 0. So let's go ahead and plug in 0 there. All right, so keep in mind the limit. One of the most important things to know about the limit is that it doesn't matter what happens at the point. It only matters what happens near the point. So look at these three graphs that we're looking at here. So notice here we've got a filled in circle. Here we've got an open circle. And here we've got an open circle with a dot somewhere else. And the idea here is if I look at the limit in all three of these cases, the limit as x approaches a of f of x is going to equal L in all three of these cases. So what happens at the point isn't going to matter. So notice, let's just take a pen. Let's pretend we can't see what happens at the point. So if I just color in so I can't see what happens at the point. Notice when I do that, do the functions look different at all? No, they look identical. The only thing that's different is what happens at A. In the first one, it's defined at A. At the second one, it's not defined at A. In the third one, it's defined at A, but not it's not continuous. It's at somewhere else. But all those cases, the limit is the same. So the key thing to keep in mind is, again, it doesn't matter what happens at the point. It only matters what happens near the point. So let's look at number 3 here. Find the limit as x goes to -2. So as x goes to -2, what is y getting close to? So here's -2. So as I approach there, again, from the left side, it looks like I'm getting there. From the right side, it looks like I'm getting there. So it looks like I'm going to be approaching 5. That's my limit. So keep in mind, if I say what is f of -2, well, f of -2 is going to be that guy. That's equal to 3. But the limit is 5. All right? Doesn't matter what happens at the point, only what happens near the point. Another way, it's kind of hard for me to do it on the calculator or on the computer here, but I'd like to cover up, again, what happens here. Let's cover it up. So we have no idea what that is. If you were to guess where the function is, where would you guess it would be? You would guess it would be right there at 5. That's the limit. So similarly, so f of -2, sorry, I wrote that down there. F of -2 is equal to 3. That's what we did right there. So that's the actual point. The limit is what we're looking at. So real quickly, what's the limit as x approaches 4? X approaches 4, that'd be 7. F of 4 is 2. Finding a limit by graphing a function. So let's graph this function and use the graph to find the limit as x goes to 3 of f of x. So 2x minus 4, that has a y-intercept of -4. And that's everywhere where x is not equal to 3. So I have a slope of 2. So I'm going to go up here. It's not defined there, but so let's have an open circle there. And that's an awful straight line. Let's try that one more time. A little bit better. All right, so that's what 2x minus 4 looks like, and then it's defined to be, I'll do that one in green, so just so we kind of have a little colored code here. So when x equals 3, it's f of x equals 3 as well. So I got a filled in circle there. So looking at that, what's the limit? Well, the limit is 2, because it looks like we're approaching 2. Remember, it's the y value. As x approaches 3, y approaches 2. So my limit as x approaches 3 is 2. Now, one thing to kind of keep in mind here is, remember what I said, is it doesn't matter what happens at the point, only what happens near the point. So if I look at this, I could not know what this is at all. That wouldn't matter. And I see that if I plug 3 into this guy, I get 2 times 3 minus 4 gets me 2. That ends up being my limit, because what happens at the point doesn't matter. Only what happens near there. So one-sided limits. So left-handed limit, we use the notation limit as x approaches a. We have a little minus sign in the exponent kind of area. And that's just meaning from the number smaller than a. So it's from the left. And then the right-hand limit is x goes to a with the plus sign of f of x. And again, that's just the plus sign meaning numbers bigger than a, to the right of a. So looking at this picture here, the limit from the left is, we're just going to follow along here. The limit from the left looks like it's 4, because as I come from the left side, it looks like my y value is hitting 4. The limit from the right side also looks like it's 4. And so in that case, I would just say the limit as x approaches 2 of f of x equals 4. Now, if we look at the next example here, from the left, as we come along here, look where it's pointing. It's pointing at 2. So if I were to say what the limit as x approaches 1 from the left of f of x, I would say that that's equal to 2. The limit as x approaches 1 from the right, actually let's do that in green. And there's a little extra mark there, just make sure it's not -1, it's just negative. So f of x. And now if I look from the right side, it looks like we're coming here, it looks like we're pointing at 4. So in this case, if I said what is the limit as x approaches 1 of f of x. So from the left it was 2, from the right it was 4. This would be does not exist, undefined. And we're going to talk about that right down here. So one-sided limits can be used to show that a function a has a limit as x approaches a. So limit as x approaches a, as limit as x approaches a of f of x equals L, if and only if both limit as x goes to a from the left equals L and limit as x goes to a from the right equals L. So basically what that's saying is this limit here only exists if these both exist and these guys match. If they don't match, it doesn't exist. If they do match, it does exist, and that's the limit. So one-sided limits can be used to show that a function a has no limits as x approaches a. If from the left it equals L, from the right it equals m, and L is not equal to m, then this does not exist. So if the left and right hand match, that's the limit. If they don't match, then the limit doesn't exist. The left-hand limit does, the right-hand limit does, the limit itself does not. So let's do a bunch of practice here. So use the graph of the piecewise function f to find each of the following or state that the limit or function does not exist. So 0 from the left, notice as I go from the left to 0, it looks like I'm pointing at 2. Limit as 0 from the right, looks like I'm pointing at 1. Doesn't matter, open circle, closed circle, doesn't matter at all. Limit as x approaches 0, well, these two guys don't match, so that does not exist. Looking at this, again, from the right side I'm pointing here, from the left side I'm pointing here. My arrows are not pointing at the same number, so therefore it does not exist. F of 0 is equal to 1 though. So the limit does not exist, but the function does in this case, because that's a filled in circle there. And that's our introduction to limits. I encourage you to ask questions. I'm hoping to use our time, our in-class time, to kind of explain some more of the intuition and things like that. This is very much a topic that requires some back and forth. But there's kind of your overview of how to get started.